What if 3i Atlas turns out to be a Black Swan event, a cosmic accident that changes history forever? They said it was just another interstellar wanderer, a frozen relic from nowhere, drifting quietly past the sun, leaving nothing behind but data and dust. But then, it didn't leave. It began to accelerate, not randomly, deliberately. Its speed shifted, its brightness pulsed, as if something unseen was steering it. And that's when the math failed. The equations broke. What was once predictable became impossible. Astronomers call it an anomaly. But what if it's more than that? What if this is a 1 in a billion moment, the kind that rewrites everything we know about gravity, time, and coincidence itself? Stay awake, because tonight you'll understand why something that may never happen again in the existence of our planet might be happening right now. If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about this new possibility. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. Latest breaking anomalies. Imagine this. Telescopes swiveling in unison across continents, orbit plots flickering on screens in dark control rooms, a burst of water vapour erupting from a frozen traveller millions of miles from the sun. Headlines flashing across news feeds, alien tech, unexpected acceleration. Something we've never seen before. This is not science fiction. This is happening right now, and it has a name. 3i Atlas, an interstellar comet discovered in July 2025 that was supposed to behave like every other chunk of ice and rock we've catalogued. Predictable, quantifiable, safe. But 3i Atlas isn't following the script, and the deeper we look, the stranger it becomes. When astronomers first spotted this visitor from beyond our solar system, they expected it to follow the playbook written by its predecessor, 1i/Oumuamua. They thought they knew what to watch for. Outgassing, brightening as it approached the sun, a trajectory bent slightly by jets of sublimating ice. Nothing alarming, nothing that would keep anyone awake at night. But within weeks of discovery, the data started to diverge from predictions, and now, months later, we're staring at something that doesn't quite make sense. Let me give you one example that should make your skin prickle. This comet is shedding water like a fire hose, not near the sun, where you'd expect frozen volatiles to vaporize. No, at roughly 2.9 astronomical units from the sun. That's almost 3 times the distance between Earth and our star. Out there, most comets are dormant, quiet, frozen solid. But 3i Atlas is active, violently active, and nobody can fully explain why. The James Webb Space Telescope turned its infrared eyes toward this object and found something even more peculiar. The coma, that glowing cloud of gas and dust surrounding the nucleus, is dominated by carbon dioxide. Not water, carbon dioxide. And the ratio of carbon dioxide to water is approximately 8:1. That makes it one of the highest carbon dioxide to water ratios ever observed in a comet. Ever. In the history of cometary science. Think about that. We've studied hundreds of comets. We've catalogued their chemistry. We've built models. And then this thing arrives from interstellar space and breaks the pattern. So here's the core tension. If this is a comet, a natural body made of ice and rock, why is it so active so far from the sun? Why is its chemistry so extreme? And if it isn't fully natural, if there's even a sliver of possibility that it's something else, what then? Some astronomers are starting to whisper a term you usually hear in financial markets and epidemiology, Black Swan. An event so rare, so unpredictable, that it rewrites the rules after it occurs. Now I know what you're thinking. Comets are weird. Space is full of outliers. But consider this. Astrophysicist Avi Loeb, the same scientist who suggested Oumuamua might be artificial, has pointed out that 3i Atlas shows non-gravitational acceleration anomalies that don't fit standard models. When a comet outgasses, the jets push it off course. That's normal, that's expected. But 3i Atlas isn't accelerating the way it should. Or maybe it is accelerating, but the forces don't match the observed outgassing rates. Either way, something doesn't add up. And when basic physics doesn't add up, you have to start asking uncomfortable questions. Let me show you its path. This object is travelling on a hyperbolic orbit. That means it came from interstellar space, and it will leave our solar system forever. It's moving retrograde, meaning it orbits the Sun in the opposite direction of the planets. Its inclination relative to the ecliptic, the plane where most planets orbit, is only about 5 degrees. That might not sound significant, but statistically it's unusual. Most interstellar objects should arrive from random angles, but this one came in almost aligned with our planetary disk, almost as if it knew where to aim. Perihelion, the closest approach to the Sun, occurred on October 29, 2025, just days ago. Right now, as you're hearing this, 3i Atlas is rounding the Sun and beginning its outbound journey, and scientists are scrambling to gather every scrap of data before it fades into the cosmic background. But here's the question that should keep you awake tonight. Could this object trigger a cascade of surprises? Could it already be disturbing our assumptions about what's possible? Could it be the first domino in a sequence we haven't even imagined yet? Because if 3i Atlas is a black swan, then by definition, we won't recognise it as one until after the consequences unfold. Over the next 2 hours, we're going to examine whether 3i Atlas is simply exotic, a statistical outlier in an infinite universe, or whether it's quietly rewriting the rules of space. We're going to explore 8 scenarios, ranging from plausible to wildly speculative. Some are grounded in orbital mechanics and observational astronomy. Others venture into territory that will make skeptics roll their eyes. But that's the point. A Black Swan event isn't supposed to be obvious. It's supposed to be invisible until the moment it changes everything. We'll look at orbital perturbations that could cascade decades from now. We'll consider fragmentation events that might seed future threats. We'll ask whether this comet could interact with the Sun in ways we've never witnessed. We'll examine the possibility of artificial signals buried in noise. We'll explore atmospheric anomalies, disclosure cascades, psychological shockwaves, and even reality glitches, moments when the instrumentation itself might reveal cracks in our understanding of time and space. And here's the uncomfortable truth. We might already be inside the Black Swan event. We might be watching it unfold in real time, misinterpreting it as curiosity rather than catastrophe, because that's how these events work. They only make sense in hindsight, after the paradigm has shifted, after the rules have changed, after it's too late to prepare. So let's begin. Let's pull back the layers. Let's examine the data, the speculation, the fear, and the wonder. Let's ask the question nobody wants to ask out loud. What if 3i Atlas isn't just passing through? What if it's the beginning of something we can't yet name? Part 2, Observed Deviations from Expectation. Before we dive into the anomalies, we need to establish a baseline. We need to understand what normal looks like, because the only way to recognise a deviation is to know what you're deviating from. And in the case of interstellar comets, we actually have a pretty good idea of what to expect, or at least we thought we did. When a comet approaches the Sun, solar radiation heats its surface. Ice sublimates, turning directly from solid to gas. That gas escapes through cracks and vents in the nucleus, carrying dust particles along with it. This process creates the coma, the glowing atmosphere, and sometimes a tail stretching millions of miles behind the comet. The jets of gas also act like tiny rocket engines. They push the comet slightly off its gravitational trajectory. This is called non-gravitational acceleration, and it's predictable. Given the comet's distance from the Sun, its size, and its composition, astronomers can calculate how much it should deviate from a purely gravitational path. Comets also brighten as they approach the Sun. This brightening follows a power law. The closer they get, the more active they become, and the brighter they appear. Scientists use something called the heliocentric distance exponent to describe this relationship. For most comets, this exponent falls within a certain range. If it's too high or too low, it suggests unusual composition or behaviour. So that's the baseline. Outgassing increases closer to the Sun. Brightness follows predictable curves. Non-gravitational forces match outgassing rates. Photometric behaviour aligns with distance. Simple, testable, reliable. Now let's talk about 3i Atlas. At approximately 2.9 astronomical units from the Sun, it was already shedding water at rates typically seen much closer to the Sun. Imagine turning on a faucet in deep freeze and watching water pour out anyway. That's essentially what's happening here. Most comets at that distance are dormant. Their surfaces are too cold for significant sublimation. But this comet doesn't seem to care about our models. The James Webb Space Telescope measured the composition of its coma and found something extraordinary. Carbon dioxide dominates. The ratio of carbon dioxide to water is about 8:1. To put that in perspective, most solar system comets have ratios closer to 1:10 or 1:20. Water is usually the dominant volatile, but not here. Here, carbon dioxide is king, and nobody knows why. Is the nucleus unusually rich in carbon dioxide ice? Did it form in a colder, more carbon-rich region of its parent star system, or is something else releasing the carbon dioxide in a way we don't understand? Dust production is another oddity. Observations from the Nordic Optical Telescope measured how dust production scales with distance. The power law index came out to approximately 3.8, plus or minus 0.3. That number tells us how sensitive the comet is to solar heating. A higher index means rapid changes in activity. A lower index means gradual changes. 3I Atlas falls within a known range, but it's on the high end. It's reacting strongly to solar radiation. More strongly than we'd expect for an object of its assumed composition. Then there's the polarimetry. When sunlight scatters off dust particles in the coma, it becomes polarized. The degree and angle of polarization depend on the size, shape, and composition of the dust grains. Astronomers observed 3I Atlas and found what they called extreme negative polarization. That's a fancy way of saying the polarization behavior doesn't match known solar system comets. The phase angle dependence, the way polarization changes as the viewing angle shifts, is unusual, different, anomalous. Now let's talk trajectory. 3I Atlas is on a hyperbolic orbit with an eccentricity greater than 1. That means it's not bound to the Sun. It will escape. Its inclination relative to the ecliptic is about 5 degrees, and it's moving retrograde. That combination is statistically rare. Most interstellar objects should arrive from random directions. The fact that this one came in nearly aligned with the plane of the planets is, well, coincidental. Maybe. But coincidences in astronomy often hide deeper truths. Perihelion occurred on October 29, 2025. Right now, the comet is moving outbound. On October 3, 2025, it passed within roughly 0.19 astronomical units of Mars. That's close. Closer than many near-Earth asteroid encounters. On November 3rd, it will pass within 0.65 astronomical units of Venus. And in March 2026, it will pass within 0.36 astronomical units of Jupiter. These close approaches don't pose a collision risk, but they do raise questions about gravitational interactions. Could this object perturb the orbits of smaller bodies? Could it nudge an asteroid into a different path? We'll come back to that question later. Here's where things get truly strange. Despite heavy outgassing, despite the water and carbon dioxide pouring off its surface, 3I Atlas does not show the expected non-gravitational acceleration, or at least the acceleration is much weaker than models predict. A.V. Loeb has pointed out that this suggests the nucleus must be very massive or very dense. If the jets are pushing against a large mass, the acceleration will be small. But if the nucleus is small and the outgassing is weak, where's all that water coming from? The numbers don't fit. The forces don't balance. Something is missing from the equation. Size estimates are all over the place. Depending on assumptions about reflectivity and composition, the nucleus could be anywhere from 0.32 kilometers to 5.6 kilometers in diameter. That's a huge uncertainty, and that uncertainty propagates through every calculation we make. If the nucleus is small, the outgassing rates are absurd. If it's large, the lack of acceleration is absurd. Either way, absurdity. So what does this mean? If outgassing is supposed to push the object off trajectory but it doesn't deviate much, we have a few options. Maybe the jets are symmetrical, cancelling each other out. Maybe the nucleus is rotating in a way that distributes thrust evenly. Maybe the material being ejected is so slow-moving that it doesn't impart much momentum. Or maybe, just maybe, the nucleus is denser than anything we've seen before. Denser than rock, denser than iron, dense enough to make you wonder what it's made of. And that brings us to the uncomfortable question. Is this just a weird comet? Or is it the first sign of something far more unpredictable? Because if we can't explain its behavior with standard models, then our models are incomplete. And if our models are incomplete, what else have we missed? Part 3. Media and Community Reaction. Speculative Framing. The astronomical community is divided. On one side, you have the cautious establishment, scientists who've spent careers studying comets, people who trust the data, who wait for peer review, who resist sensationalism. On the other side, you have the provocateurs, researchers willing to entertain low-probability, high-impact hypotheses, people who think the universe might still have surprises left. And in the middle, you have the media, amplifying both voices, sometimes responsibly, sometimes recklessly. NASA's lead scientist for solar system small bodies, Tom Statler, went on record saying that 3I Atlas behaves like a comet. He emphasized that the evidence is overwhelmingly pointing toward a natural body. Water outgassing, dust production, photometric behavior consistent with sublimation, all the hallmarks of a comet. Nothing to suggest anything artificial or exotic, just a chunk of ice from another star system doing what chunks of ice do. But then you have Avi Loeb, the Harvard astronomer who became a household name after suggesting Oumuamua might be a light sail. Loeb has been vocal about 3I Atlas. He's pointed out the acceleration anomalies. He's questioned the assumptions underlying our models. And he's urged the scientific community not to dismiss low-probability hypotheses without investigation. He's not saying it's aliens. He's saying we should look, because if we don't look, we'll never know. And then there's the media. Tabloids ran headlines about hostile alien tech in disguise. Major outlets picked up on the Black Swan framing, calling it a rare object that could change everything. The Guardian published pieces balancing scientific caution with public curiosity. Live Science explored the possibility of artificial origins, framing it as unlikely, but not impossible. EFL Science covered Loeb's comments, emphasizing the importance of ruling out exotic explanations through observation, not assumption. The Times of India called 3I Atlas a rare black swan object, and referenced an international observation campaign coordinated by the International Asteroid Warning Network. IARPUN, a coalition of telescopes and space agencies dedicated to detecting and tracking near-Earth objects. The fact that they're involved suggests this object is being taken seriously, not as a threat, but as something worth watching closely. So why would scientists entertain alien tech narratives at all? Why risk credibility by engaging with speculation? Because the stakes are asymmetric. If you ignore a low-probability event and it turns out to be real, the consequences are catastrophic. But if you investigate and find nothing, you've only wasted time and resources. This is the logic of Pascal's wager applied to astronomy. The cost of being wrong is higher than the cost of looking foolish. But there's a darker side to this framing. Speculation breeds fear. It attracts conspiracy theorists. It blurs the line between responsible inquiry and irresponsible fear-mongering. When mainstream outlets start using phrases like alien tech and black swan, they're not just reporting. They're shaping perception. They're influencing how the public, and even policymakers, respond to uncertainty. Think about it. What if 3I Atlas is completely benign? What if it's just a comet with unusual but explainable chemistry? But because of the speculation, because of the framing, resources get diverted. Telescopes get pointed at it instead of other targets. Planetary defense budgets get debated. International collaborations form around a non-threat. And all because we couldn't distinguish between caution and paranoia. On the other hand, what if the speculation is warranted? What if there's even a 1% chance that this object is something unprecedented? Then ignoring it would be negligent, dangerous, a failure of imagination and duty. Because the whole point of a black swan is that it's unpredictable. You can't prepare for it by following the old rules. You have to be willing to consider the impossible. This tension plays out in funding decisions, in telescope time allocation, in how seriously space agencies take follow-up observations. If an object is labelled a curiosity, it gets minimal attention, but if it's labelled a potential black swan, suddenly everyone wants a piece. Careers can be made or broken depending on whether the hype is justified. And there's a psychological dimension too. Why are people so fascinated by this? Why does the idea of an interstellar visitor spark both wonder and dread? Maybe because it reminds us how small we are, how fragile our understanding is, how much of the universe remains unknown, or maybe because deep down we're waiting for something to break the monotony, waiting for proof that we're not alone, or proof that the cosmos is stranger than we ever imagined. The black swan concept isn't just scientific, it's cultural. It's about how we respond to the unknown. Do we dismiss it as noise? Do we investigate it as signal? Do we let fear drive us or curiosity? Because once a Black Swan event occurs, once the paradigm shifts, you can't go back. You can't unsee it, you can't unknow it. The world is different afterward, and that difference is irreversible. So here's the question. Are we hyping 3i Atlas into something it's not? Or are we finally taking seriously the possibility that space can still surprise us? Because the answer to that question will determine how we respond to the next anomaly, and the one after that, and the one after that. But to decide whether this is hype or real threat, we must first define what a space Black Swan would even look like. Because without a framework, without criteria, we're just guessing. And guessing isn't good enough, not when the stakes might be this high. Part 4. Defining what a space Black Swan could be. The term Black Swan comes from the philosopher and statistician Nassim Taleb. He used it to describe events that are rare, unpredictable, and have massive consequences. Events that seem obvious in hindsight, but were invisible beforehand. The classic example is the 2008 financial crisis. Experts assured everyone that the system was stable, risk was diversified, leverage was manageable, and then the system collapsed. And afterward, everyone could see the signs, but before, the signs were noise. Taleb argued that Black Swan events share 3 characteristics. First, they lie outside the realm of regular expectations. Nothing in the past can convincingly point to their possibility. Second, they carry extreme impact. They change industries, societies, or entire worldviews. Third, despite being unpredictable, human nature compels us to invent explanations after the fact, making them seem explainable and predictable. We retrofit causality. We say we should have seen it coming, but we didn't, and we couldn't have. So how do we translate that into astronomy? What would qualify as a Black Swan in space? A comet that triggers cascading orbital effects, an object that reveals unknown physics, a signal that confirms intelligence, a disturbance so subtle it only becomes visible decades later. Let me propose a working set of criteria. A space Black Swan must exhibit at least 3 of the following. First, unpredictability beyond current models, not just unusual, not just rare, but genuinely outside the parameter space of existing theories. Second, high potential impact on planetary safety, on scientific understanding, on detection systems, or on human perception of our place in the universe. Third, irreversible consequences, orbit shifts that persist for millennia. Data integrity loss, new understanding that invalidates old textbooks. Fourth, evidence of intentionality or physics anomalies beyond natural randomness, a signal that can't be explained by known astrophysical processes, a trajectory correction that defies inertia, a timing coincidence too precise to dismiss. Now, let's apply these criteria to 3i Atlas. Does it meet any of them already? Well, it's unpredictable in the sense that its behaviour doesn't perfectly match models. But is it beyond current models, or just at the edge? That's debatable. Does it have high potential impact? Scientifically, yes. It's challenging our assumptions, but practically it's not threatening Earth. Not directly. Does it show irreversible consequences? Not yet. And evidence of intentionality? None. At least not that we've detected. So by these criteria, 3i Atlas isn't a Black Swan. At least not yet. But it could become one. If it does something unexpected, if it fragments in a strange way, if it perturbs another object, if we detect a signal, if any of a dozen unlikely scenarios unfold, then retrospectively, we'll say it was a Black Swan all along. And that's the paradox. You can't identify a Black Swan before it happens. You can only prepare for the possibility. You can only build systems robust enough to withstand surprises. You can only cultivate a mindset that treats the improbable as worth investigating. So what are the scenarios? What are the specific ways 3i Atlas could become a Black Swan? I've identified 8. Some are grounded in physics, some are speculative, some are borderline metaphysical. But each represents a different flavour of catastrophe, a different path from curiosity to crisis. The first scenario I call orbital domino. A small gravitational nudge cascades into orbital shifts for other objects. Maybe 3i Atlas perturbs an asteroid as it passes Mars. That asteroid's orbit changes slightly. Over decades, that change compounds. Eventually, the asteroid crosses Earth's path, and we never saw it coming because we didn't track the original perturbation. Second scenario is fragmentation event. The comet breaks apart in an unusual way. Maybe one fragment shows directed motion. Maybe it decelerates against the outgassing direction. Maybe it exhibits behavior that suggests internal structure, or propulsion, or something we can't explain. Third scenario is solar disruption. Some solar activity, a coronal mass ejection or a flare, coincides with the comet's perihelion passage in an uncanny way. Maybe there's feedback. Maybe the comet triggers the event. Maybe the timing is too perfect to be random. And maybe satellites go offline, communications black out, auroras where there shouldn't be auroras. Fourth scenario is artificial signal. Telescopes detect a narrowband pulse, too brief to confirm, too weak to repeat, buried in noise until someone runs the right algorithm, and then the question becomes, do we announce it? Do we follow up? Or do we bury it because the implications are too destabilizing? Fifth scenario is atmospheric anomaly. The comet passage triggers or coincides with unexpected disturbances in Earth's upper atmosphere. Ionospheric spikes, GPS signal delays, auroras out of season, or similar effects detected by Mars orbiters. Transient, subtle, but measurable. Sixth scenario is disclosure cascade. Invisible leaks, coordinated agency statements, data releases timed with the object's flyby. Maybe it's benign, maybe it's standard scientific coordination, or maybe it's the beginning of a controlled information release. A soft disclosure, a way to prepare the public for something bigger. Seventh scenario is psychological singularity. Mass attention creates a social cascade, synchronicity, heightened anxiety, collective belief that something is about to happen. And because everyone believes it, decisions get made, policies shift, funding flows, careers pivot, and the object becomes significant not because of what it is, but because of what we think it might be. Eighth scenario is reality glitch, an extreme speculative scenario, slight desynchronization of instrumentation, pulsar timing residuals, spacecraft telemetry anomalies, atomic clock drift, all aligned with the comet's transit. As if the object is disturbing space-time itself, or revealing a flaw in our understanding of time, each of these scenarios asks a different question. Could a fragment redirect an asteroid decades from now? Is it possible we already recorded a signal that vanished before we realized its significance? Could a comet interact with the sun in ways we've never witnessed? Could public perception create a self-fulfilling prophecy? Some of these are scientifically grounded. Orbital perturbations are real. Fragmentation happens. Others are cinematic, borderline paranoid. But that's the point. A black swan isn't supposed to be the most likely outcome. It's supposed to be the overlooked one. The scenario everyone dismissed because it seemed too implausible, until it wasn't. In the next sections, we're going to examine each scenario in detail. We're going to ask which remain plausible, given current data, which are ruled out, which are unknowable, and which might already be unfolding without our awareness, because if even one of these turns out to be real, our understanding of space will never be the same. Part 5, Scenario Preview, the 8 Strange Possibilities. Let's walk through these scenarios one by one, not in exhaustive detail yet, that comes later, but enough to understand what each one entails, enough to feel the weight of possibility, because each scenario represents a different way the universe could surprise us, and each one carries consequences we're not prepared for. Scenario 1 is orbital domino. Imagine 3I Atlas passing near Mars on October 3rd, 2025. It doesn't hit anything, it doesn't collide, but its gravitational field tugs on a small asteroid, just slightly. The asteroid's velocity changes by a fraction of a meter per second. That sounds insignificant. It is insignificant. Today. But orbits are sensitive systems. Small changes compound over time. 10 years later, that asteroid's path has drifted. 20 years later, it crosses a different orbit. 30 years later, it's on a collision course with Earth. And we never connected the dots because we didn't track the original perturbation. Could 3I Atlas trigger a cascade like this? Could it nudge something into a future threat? The math says it's possible. Unlikely, but possible. Scenario 2 is fragmentation event. Comets break apart all the time. Thermal stress, rotation, structural weakness. It's normal. But what if one fragment behaves oddly? What if it decelerates when it should accelerate? What if it changes direction against the outgassing jets? Imagine astronomers detecting a secondary brightness spike weeks after perihelion. They assume it's a fragment. But when they calculate its trajectory, The numbers don't work. The fragment's momentum doesn't match the expected ejection velocity. It's moving as if something pushed it, or steered it. Is that possible naturally? Maybe, but it would require internal structure, cavities, pressure differentials, or something else, something we haven't considered. Scenario 3 is solar disruption. The sun is active. Coronal mass ejections happen regularly. Solar flares erupt. But what if one happens during perihelion? What if the timing is too perfect? What if the comet's passage coincides with a massive CME aimed directly at Earth? Satellites fail. Power grids fluctuate. Auroras appear at the equator. And scientists scramble to explain whether it's coincidence or causation. Could a comet trigger a solar event? Mainstream astrophysics says no. The comet is too small. The sun is too massive. But what if there's feedback? What if the comet's ionized coma couples with the sun's magnetic field in an unexpected way? What if we're wrong about the thresholds? Scenario 4 is artificial signal. Radio telescopes scan the sky constantly. They record data. They filter noise. They look for patterns. But what if a signal was already recorded and missed? What if 3i Atlas emitted a brief pulse during perihelion? What if it was behind the sun, making follow-up impossible? What if the signal was dismissed as interference? Imagine a postdoc running archival data through a new algorithm years from now, and finding something, a narrow-band emission, structured, non-random, pointing back to this moment, this object. Would we announce it? Would we believe it? Or would we bury it because the implications are too dangerous? Scenario 5 is atmospheric anomaly. Earth's ionosphere is sensitive to solar wind and cosmic rays, but it's also sensitive to charged particles from comets. What if 3i Atlas's coma interacts with Earth's magnetosphere? What if GPS signals show unusual delays? What if ionospheric monitoring stations detect spikes in ion density? What if Mars orbiters observe transient auroras during the October 3rd close approach? These effects would be subtle, easy to dismiss. But if multiple independent instruments detect something during the same time window, coincidence becomes correlation, and correlation demands explanation. Scenario 6 is disclosure cascade. The International Asteroid Warning Network coordinated an observation campaign for 3i Atlas. That's public knowledge. But what if there were other meetings? What if space agencies shared data quietly? What if archival anomalies were re-released during this period? Not because of conspiracy, but because this object justified a closer look at old data. And what if that closer look revealed discrepancies? Timing residuals in spacecraft telemetry, unexplained trajectory deviations in other missions, nothing definitive, but enough to make people wonder, enough to start a cascade of questions. Scenario 7 is psychological singularity. This one is harder to quantify. It's not about physics, it's about perception. What if enough people believe something is about to happen? What if social media amplifies speculation? What if policymakers start taking it seriously? What if emergency meetings get convened? What if funding gets redirected? The object becomes significant not because of what it does, but because of what we think it might do. And in a strange way, our belief changes reality, not the object's reality, but our societal reality. Decisions get made, careers pivot, history shifts, all because we couldn't separate signal from noise. Scenario 8 is reality glitch. This is the wildest scenario, the one that ventures into territory most scientists won't touch. What if multiple independent sensors recorded timing anomalies during the comet's passage? Pulsar timing residuals, atomic clock drift, spacecraft telemetry delays, all slight, all within noise margins, but all aligned with 3i Atlas's perihelion. What would that mean? Could ionized dust alter signal propagation? Could charged particles interfere with time distribution systems? Or could it reveal something deeper? A flaw in our synchronization, a wrinkle in space-time, a hint that our clocks aren't measuring what we think they are. Now, let's be clear. Most of these scenarios are unlikely. Some are nearly impossible. But the point isn't probability. The point is consequence. A black swan doesn't announce itself. It hides in the tail of the distribution. It waits in the noise. And it only becomes obvious after it happens. Over the next several sections, we're going to examine each scenario in detail. We're going to ask which ones have evidence, which ones are testable, which ones are pure speculation, and which ones might already be unfolding without our awareness. Because if we're inside a Black Swan event right now, the only way to know is to look, and to keep looking until the picture becomes clear, or until it's too late. Part 6. Scenario 1 and 2. Examined orbital domino plus fragmentation event. Let's start with the most plausible scenarios, the ones grounded in known physics, the ones that don't require exotic hypotheses or conspiratorial thinking, because if 3i Atlas is going to surprise us, it will probably do so in a way that's subtle, delayed, hidden in the mathematics of orbital mechanics. Orbital domino is the scenario that keeps planetary defense scientists awake at night, not because it's likely, but because the consequences scale over time, and by the time you notice the problem, it's too late to prevent it. Here's how it works. 3i Atlas is travelling through the inner solar system. As it passes near planets and large asteroids, its gravitational field exerts a tiny tug, infinitesimal, negligible in the short term. But orbits are chaotic systems. They're sensitive to initial conditions. A small change in velocity can propagate into a large change in position over decades. On October 3rd, 2025, 3i Atlas passed within roughly 0.19 astronomical units of Mars. That's about 28 million kilometres. For context, the Moon is only 384,000 kilometres from Earth. So this was a relatively close encounter by astronomical standards. Did it perturb anything? Almost certainly. Mars has two small moons, Phobos and Deimos. Their orbits are already unstable on geological timescales. A passing object could nudge them slightly. Would we notice? Probably not immediately. The changes would be subtle, but over years the deviations would compound. Now, Mars also has a population of co-orbital objects, asteroids that share its orbit, Trojans. These objects are gravitationally shepherded by Mars, orbiting at stable Lagrange points. But stability is relative. A perturbation could shift one of these asteroids out of its Lagrange point, and once it's out, its trajectory becomes unpredictable. It could drift inward toward Earth, or outward toward the asteroid belt, or into a resonance with Jupiter that amplifies its eccentricity. Let's talk numbers. Suppose 3i Atlas has a mass of 10 to the 14 kilograms. That's roughly the mass of a mountain, a small comet nucleus. Its gravitational influence at a distance of 0.2 astronomical units would be minuscule. But minuscule doesn't mean zero. Gravitational force falls off with the square of distance, but it never vanishes. Every object in the solar system exerts a force on every other object, and those forces add up. Now, consider an asteroid with a semi-major axis of 2 astronomical units. That's a main belt asteroid. Its orbital period is about 3 years. If 3i Atlas perturbs its velocity by just 1 millimeter per second, that sounds like nothing. But over 10 orbital periods, 30 years, that 1 millimeter per second translates into a position change of hundreds of kilometers. And if that asteroid happens to be on a trajectory that could eventually cross Earth's orbit, those hundreds of kilometers might be the difference between a miss and a hit. Planetary defense networks track near-Earth asteroids. They catalogue their orbits. They predict close approaches, but they don't track every asteroid. The ones too small or too dim slip through, and they definitely don't account for perturbations from interstellar visitors. Because until Oumuamua, interstellar visitors were hypothetical. Now they're real, and if they're real, they can perturb orbits. And if they can perturb orbits, we need to account for them. So the question is, could 3i Atlas have nudged something into a future threat? The answer is, we don't know. We don't have complete orbital data for every small body in the solar system. We don't have the computational resources to model every possible perturbation. And we don't have the telescopic coverage to detect subtle changes in trajectories. The gaps in our knowledge are vast, and those gaps are where black swans hide. Now let's talk fragmentation event. Comets fragment all the time. It's one of the most common things they do. Thermal stress from solar heating causes the nucleus to crack. Rotation generates centrifugal forces that pull weakly bound material apart. Pockets of volatile ice sublimate beneath the surface, creating pressure that blows out chunks of material. We've observed dozens of cometary fragmentations. Shoemaker-Levy 9 famously broke into multiple pieces before slamming into Jupiter in 1994. Comet Schwarzmann-Wachmann 3 has fragmented repeatedly over decades, so fragmentation itself isn't anomalous. But what if the fragmentation behaviour is anomalous? What if one fragment doesn't behave the way physics says it should? Imagine this. 3i Atlas is outgassing. Jets are firing from its nucleus. Those jets impart momentum. If a fragment breaks off, it should inherit the parent body's velocity plus the ejection velocity from the breakup. We can calculate what that should look like. We can predict the fragment's brightness, its trajectory, its evolution over time. But what if a fragment doesn't match predictions? What if it decelerates when it should accelerate? What if it changes direction in a way that outgassing jets can't explain? That would be strange. Not impossible, but strange. You'd need to invoke internal structure. Maybe the fragment has cavities that channel gas in specific directions. Maybe it's tumbling in a way that creates asymmetric thrust. Maybe it's mostly dust with very little ice, so the outgassing is weak but present. Or maybe it's something else. Maybe there's a mechanism we don't understand, a propulsion effect buried in the physics of cometary activity. Or, in the most extreme interpretation, maybe it's not entirely natural. Maybe there's something inside directing the motion. I'm not saying that's likely. I'm saying that if a fragment behaved that way, we'd have to consider it. Has 3I Atlas fragmented? As of perihelion, on October 29th, 2025, there were no confirmed reports of fragmentation. But that doesn't mean it won't happen. Comets often fragment during or after perihelion when thermal stress is highest. Follow-up observations over the coming weeks will be critical. If brightness suddenly increases, if multiple components appear in images, if the trajectory shows unexpected deviations, those would be signs. And here's the unsettling part. If a fragment did show anomalous behaviour, how would we investigate it? Telescopes can only resolve so much detail. Spectroscopy can tell us composition, but not structure. Radar might detect rotation rates and surface features, but only if the fragment is close enough. And if it's moving away from the Sun, it's also moving away from Earth. Every day it gets fainter, harder to observe. Eventually it disappears into the cosmic background, and we're left with fragmentary data. Pun intended, incomplete measurements, unanswered questions. So could a fragment seed future risk? Could it drift into a long-period orbit that brings it back centuries from now? Could it perturb another object? Could it carry information about the parent body's structure that we'll never retrieve? Yes, to all of those. Fragmentation is unpredictable. It introduces new variables into an already chaotic system, and every new variable is a potential pathway to surprise. Let me give you a hypothetical timeline. Suppose a fragment breaks off in November 2025. Too faint to detect immediately, it drifts. Over 5 years, its orbit evolves. By 2030, it's crossing the orbit of a near-Earth asteroid. By 2040, that asteroid's orbit has shifted slightly. By 2060, the asteroid is on a collision course with a satellite constellation, and nobody connects it back to 3I Atlas because the causal chain is too long, too indirect, too buried in noise. That's the orbital domino scenario. That's the nightmare that keeps dynamicists awake. Because orbital mechanics is deterministic in theory but chaotic in practice, you can predict trajectories with exquisite precision over short timescales. But over decades, over centuries, tiny uncertainties explode into massive deviations, and you can't prevent what you can't predict. So what's the verdict on these two scenarios? Are they plausible? Yes. Are they likely? No. Do they represent black swan potential? Absolutely. Because the impact is delayed, the causality is obscured, and by the time the consequences manifest, the triggering event is ancient history. We'd have no way to trace it back, no way to say, this happened because of 3I Atlas. It would just be another asteroid, another fragmentation, another perturbation, lost in the noise of a chaotic solar system. But if we're serious about planetary defense, if we're serious about long-term survival, we have to account for these possibilities. We have to track interstellar visitors, not just during their flyby, but after. We have to model their gravitational influence on small bodies. We have to monitor for fragmentation and characterize any fragments, because the universe doesn't care about our models. It doesn't care about our assumptions. It just does what it does, and we either adapt or we suffer the consequences. Part 7, Scenario 3 and 4, Solar Disruption plus Artificial Signal. Now we're moving into territory that makes most scientists uncomfortable, not because it's physically impossible, but because it requires coincidences, timing alignments, correlations that could be random but feel too precise. And humans are notoriously bad at assessing coincidence. We see patterns where none exist. We infer causation from correlation. We construct narratives that feel true even when they're not. But sometimes coincidences aren't random. Sometimes timing matters. And sometimes the universe throws us a curveball that demands explanation. So let's explore solar disruption, the idea that 3I Atlas's perihelion passage could coincide with or even trigger solar activity in a way that affects Earth. The Sun is a chaotic system. Its surface roils with convection. Its magnetic field twists and tangles. Every 11 years the field flips polarity, driving the solar cycle. During solar maximum, sunspots proliferate. Coronal mass ejections become frequent. Solar flares erupt with energies equivalent to billions of nuclear bombs, and all of that activity sends radiation and charged particles streaming into space. When a coronal mass ejection hits Earth, it compresses our magnetosphere. Charged particles funnel down magnetic field lines toward the poles. They collide with atoms in the upper atmosphere, creating auroras. If the CME is strong enough, it can induce currents in power grids, knocking out transformers. It can disrupt satellites. It can create radio blackouts. The Carrington event of 1859 was the most powerful solar storm in recorded history. Telegraph systems caught fire. Auroras were visible at the equator. If a similar event happened today, the economic damage could reach trillions of dollars. So solar activity is real, it's dangerous, and it's unpredictable on short timescales. We can forecast the solar cycle, we can predict general trends, but we can't predict exactly when a CME will erupt or where it will be aimed. There's too much chaos in the system. Now, here's the question. Could a comet interact with the Sun in a way that triggers or amplifies solar activity? Mainstream astrophysics says no. The comet is too small. Its mass is negligible compared to the Sun. Its gravitational influence is zero. Its magnetic field, if it even has one, is trivial. There's no plausible mechanism for a comet to affect the Sun. But what about second-order effects? What about the comet's ionized coma? As 3I Atlas approached perihelion, its outgassing created a cloud of ionized gas and dust. That cloud is electrically conductive. Could it couple with the Sun's magnetic field? Could it create a feedback loop? Could it act as a trigger for instabilities that were already building in the solar corona? I'm not saying it's likely. I'm saying it's not obviously impossible. And if solar activity did spike during the perihelion window, if a major CME erupted on October 29th or 30th, if Earth experienced unusual auroras or satellite disruptions during that exact time frame, we'd have to ask whether it was coincidence. Let me check. Were there any significant solar events around October 29th, 2025? Any CMEs? Any flares? Any geomagnetic storms? If there were, the timing would be striking. If there weren't, then this scenario loses credibility. But the absence of an event doesn't mean the scenario is impossible. It just means it didn't happen this time. Because the question isn't just whether it happened, it's whether it could happen, and whether we'd recognise it if it did. Now let's pivot to artificial signal. This is the scenario that makes skeptics roll their eyes, the scenario that invites ridicule. But it's also the scenario with the highest stakes. Because if it's real, if 3I Atlas is anything other than a natural comet, everything changes. SETI, the search for extraterrestrial intelligence, has been scanning the sky for decades. Radio telescopes listen for narrowband signals. Optical telescopes look for laser pulses. Algorithms sift through noise, searching for patterns, and so far, we've found nothing definitive. The WOW signal of 1977 remains unexplained but unrepeated. Fast radio bursts turn out to be astrophysical, probably from magnetars. Every candidate signal either fades into noise or gets explained by natural phenomena. But here's the thing, SETI assumes signals will be continuous or repeating. A civilization broadcasting intentionally would want to be heard. They'd transmit for long periods. They'd aim at promising star systems. They'd use frequencies that penetrate interstellar dust. All of that makes sense if you're trying to communicate across light years. But what if you're not broadcasting? What if you're travelling? What if you're a probe, and you only transmit during perihelion, when solar conjunction provides cover? What if your signal is designed to be ambiguous? Weak enough to be dismissed as interference, brief enough to avoid confirmation, structured enough to be noticed by anyone looking closely, but only if they're looking closely. Imagine 3I Atlas emitted a pulse on October 29th. A narrowband emission, 1.42 GHz, the hydrogen line, classic SETI frequency, lasted 3 seconds. Signal strength barely above noise. Telescopes recorded it. But the data was flagged as radio frequency interference, Human-made, terrestrial, filtered out by standard algorithms. And nobody looked at it again. Years later, someone runs archival data through a new machine learning algorithm. The algorithm doesn't care about human biases, it just looks for patterns, and it finds one. A brief structured pulse, non-random, originating from the direction of 3I Atlas during perihelion. But by then, the object is gone, out past Jupiter, fading into the darkness, and there's no way to follow up, no way to confirm, no way to rule it out. Would we announce it? Would we publish? Or would we bury it? Because the implications are destabilizing. If it's real, if it's artificial, then we're not alone. And we've been visited. And we didn't recognize it at first. And that raises uncomfortable questions about how many other signals we've missed, how many other visitors we've ignored, how blind we've been. But if it's not real, if it's just noise, then announcing it causes panic. It erodes trust in science. It feeds conspiracy theories. It diverts resources from legitimate research. So the decision becomes political, not scientific. Do we tell the truth and risk chaos? Or do we withhold information and risk accusations of cover-up? This is why the artificial signal scenario is so fraught. Because it's not just about detection, it's about response. And response depends on belief. And belief depends on evidence. And evidence, in this case, might be ambiguous, incomplete, open to interpretation, and interpretation is where objectivity dies. So here's the question. If a signal was detected, would you want to know, even if it couldn't be confirmed, even if it might be wrong? Because ignorance is comfortable, certainty is comforting, but ambiguity is maddening, and sometimes ambiguity is all we get. Part 8, Scenario 5 and 6, Atmospheric Anomaly. Disclosure Cascade. Let's pull back from deep space and look at something closer to home. Earth's atmosphere, specifically the ionosphere. That tenuous layer between 100 and 1,000 kilometers altitude, where ultraviolet radiation from the sun ionizes atoms, creating a plasma. This layer is critical for radio communication. It reflects certain frequencies, allowing signals to travel beyond the horizon. It also affects GPS. Satellites send signals through the ionosphere to ground receivers, but ionized plasma delays those signals. The delay depends on electron density, so GPS systems constantly measure ionospheric conditions and correct for them. The ionosphere is sensitive to solar activity. When the sun emits a flare or a coronal mass, ejection, the charged particles interact with Earth's magnetic field, creating disturbances. These disturbances manifest as auroras. They also cause fluctuations in electron density. GPS signals become less accurate. Radio communications degrade. In extreme cases, satellites can be damaged. But the ionosphere is also sensitive to other things, meteor showers for instance. When Earth passes through a debris stream, thousands of meteors burn up in the upper atmosphere. The vaporized material ionizes, creating transient layers of enhanced electron density. These layers can reflect radio waves in unusual ways. They can cause brief disturbances in satellite signals. So here's the question. Could 3I Atlas affect Earth's ionosphere? Not through collision, it's not going to hit us. But through its coma, through the cloud of ionized gas and dust trailing behind it. Could that cloud intersect Earth's magnetosphere? Could it create a transient disturbance? The answer depends on geometry. 3I Atlas passed closest to Earth in late September, early October, at a distance of roughly 1.2 astronomical units. That's about 180 million kilometers. Too far for direct interaction, but the coma extends far beyond the nucleus, and the ion tail, driven by solar wind, can stretch for millions of kilometers. Could that tail have brushed Earth's magnetosphere? Could charged particles from the comet have funneled down magnetic field lines? I don't have data on that. I don't know if anyone was monitoring ionospheric conditions specifically during that window, but if they were, if ground-based receivers or satellites detected anomalous electron density spikes, if GPS signals showed unusual delays, if any of that correlated with the comet's passage, it would be interesting. Not conclusive, but interesting. And then there's Mars. On October 3rd, 3I Atlas passed within 0.19 astronomical units of Mars. That's much closer than Earth. Mars has orbiters, rovers, instruments. Could any of them have detected atmospheric effects? Mars has a thin atmosphere, but it has an ionosphere, and it experiences auroras, driven not by a global magnetic field like Earth's, but by localized crustal magnetic fields. If the comet's Comet interacted with Mars's ionosphere, if orbiters detected transient glows or ion spikes, that would be significant. Again, I don't have data. Maybe the data exists. Maybe it's sitting in an archive somewhere, waiting for someone to analyze it. Or maybe nobody was looking. Because why would they? 3I Atlas is a comet. It's supposed to be inert, non-threatening, so maybe the instruments weren't pointed in the right direction. Maybe the data wasn't flagged as interesting. Maybe the anomaly, if it exists, is hidden in noise. That's the frustrating thing about black swans. You don't know where to look until after the event, and by then, the moment has passed. The data is archived, the attention has moved on. Now let's talk about disclosure cascade. This scenario is less about physics and more about information, about how space agencies communicate, about what gets shared publicly and what doesn't, about the gap between observation and announcement. The International Asteroid Warning Network coordinated an observation campaign for 3I Atlas. That's public. Multiple telescopes, multiple countries, shared data. That level of coordination is normal for interesting objects. It doesn't imply conspiracy, it implies scientific collaboration. But here's where it gets murky. What if that collaboration revealed something unexpected? What if telescopes detected an anomaly? Not necessarily dramatic, not necessarily proof of anything, but enough to warrant a closer look at archival data. Enough to justify quiet meetings. Enough to trigger internal discussions about how to frame the findings. Imagine this. During the observation campaign, someone notices a discrepancy in spacecraft telemetry. Maybe a Mars orbiter recorded a slight timing offset during the October 3rd close approach. Maybe the offset is within error margins, but it's there, and it's contemporaneous with the comet's passage, so they check other data, they pull up telemetry from other missions, and they find more offsets, small, subtle, but correlated. None of it is conclusive, none of it proves anything, but it's odd enough that someone writes a memo, odd enough that a working group forms, odd enough that data gets re-released with updated calibrations, and if you're paying attention, if you're looking for patterns, you might notice. You might see the cascade beginning. I'm not saying this happened. I'm saying this is how disclosure could work in the 21st century, not a dramatic press conference, not a smoking gun, but a slow drip of information, a series of minor revelations, each one plausible on its own, each one explainable. But together they form a pattern, and the pattern suggests that something was noticed, something was discussed, something was considered significant enough to revisit old assumptions. And here's the thing. If that cascade is happening, we won't recognize it in real time. We'll only see it in hindsight, when someone connects the dots, when the timeline becomes clear, when the archived memos and data releases and quiet workshops are compiled into a narrative. And by then, the moment of disclosure will be impossible to pinpoint, because it wasn't a moment, it was a process, and processes are invisible until they're complete. So the question is, are we inside a disclosure cascade right now? Are space agencies coordinating quietly? Are archival anomalies being reevaluated? Are there meetings happening behind closed doors? Maybe, maybe not. But the fact that we can't know for certain is precisely the point, because black swans hide in uncertainty. They live in the gaps between data and interpretation, between observation and announcement, and sometimes, by the time the announcement comes, the event is already over. Part 9, Scenario 7 and 8, Psychological Singularity. Reality glitch. Now we venture into the strangest territory, the scenarios that have less to do with physics and more to do with perception, with consciousness, with the way humans respond to mystery, because sometimes the impact of an event isn't physical, it's psychological, it's social, it's the way belief shapes reality. Psychological singularity is the idea that collective attention can create consequences independent of the object itself. Think about historical precedents. When Halley's Comet appeared in 1910, some people panicked. Newspapers ran stories about Earth passing through the comet's tail. Entrepreneurs sold comet pills to protect against poisonous gases. There was no danger. The comet's tail is so diffuse it poses zero threat. But the belief in danger created real social effects: anxiety, irrational behaviour, market disruptions. The event became significant not because of what it was, but because of how people responded to it. Or consider Y2K, the year 2000 bug. Computers used 2-digit year codes. Programmers warned that systems would fail when the year rolled over from 99 to 00. Billions were spent on fixes. Contingency plans were drafted. Some people stockpiled supplies, and when midnight came, nothing catastrophic happened. Most systems worked fine, but the preparation, the fear, the collective response, those had real consequences. Resources were reallocated, careers were built, industries pivoted. So what if 3i Atlas triggers something similar? What if speculation grows? What if media coverage intensifies? What if enough people start believing that something is about to happen? Not because of evidence, but because of narrative momentum, because the story feels true, because uncertainty is uncomfortable and humans crave resolution. Imagine this. Social media erupts with theories. Forums light up. Hashtags trend. Some people claim they've dreamed about the comet. Others report synchronicities, meaningful coincidences tied to the date. Scientists issue statements trying to calm fears, but the statements are measured, cautious. They say things like, no evidence of danger instead of absolutely safe. And that hedge, that linguistic caution, gets interpreted as doubt, as hidden knowledge, as confirmation that something is being withheld. Policymakers start getting calls, journalists start asking questions, congressional aides request briefings, and suddenly, space agencies are in a position where they have to respond. Not because the comet is threatening, but because the perception of threat has momentum, and that momentum creates real-world consequences. Budgets shift, telescope time gets reallocated, emergency protocols get reviewed, not because of data, but because of belief. And here's the recursive twist. Once those consequences occur, once resources get diverted, once the object becomes the focus of international attention, it becomes objectively significant. Not because of what it is, but because of what we've made it. The belief creates the reality. The narrative becomes self-fulfilling. And years later, when historians look back, they'll say 3i Atlas was important. Because look at everything that happened. Look at the policies that changed. Look at the funding that flowed. But they'll miss the causality. Because the importance wasn't inherent, it was constructed, socially engineered through collective anxiety. That psychological singularity, the moment when attention exceeds information, when belief outpaces evidence, when the map becomes the territory. And the scariest part is, there's no way to prevent it. Because trying to prevent it requires communication. And communication feeds the narrative. Silence is interpreted as concealment. Transparency is interpreted as confirmation. There's no winning move, only damage control. Now let's talk about reality glitch. This is the scenario that pushes into metaphysical territory. The idea that 3i Atlas could reveal or create anomalies in the fabric of observation itself, in the way we measure time, in the synchronization of our instruments, in the coherence of data streams. Modern astronomy depends on precise timing. Spacecraft send signals that get time-stamped. Pulsars emit regular pulses that serve as cosmic clocks. Atomic clocks on the ground synchronize GPS satellites. All of these systems assume that time flows uniformly, that clocks tick at predictable rates, that the universe operates on a consistent timeline. But what if there are glitches? What if under certain conditions timing systems desynchronize? What if multiple independent instruments recorded minute discrepancies during the same window? Microsecond offsets, nanosecond residuals, all aligned with 3i Atlas's perihelion passage. Is that physically plausible? Maybe. Ionized plasma can affect signal propagation. Charged particles can interfere with electronics. Extreme gravitational fields can cause relativistic time dilation. But 3i Atlas isn't extreme. Its mass is negligible. Its gravitational field is trivial. There's no obvious mechanism for it to affect timekeeping on Earth or in spacecraft. Unless there's something we're missing. Unless the comet's coma creates an electromagnetic environment that interacts with our instruments in subtle ways. Unless the timing offsets are real and measurable, but fall below our detection thresholds until someone specifically looks for them. Imagine someone runs a statistical analysis on pulsar timing data from October 2025. They're looking for gravitational wave signals. They're comparing arrival times across multiple observatories, and they notice something odd. A cluster of residuals, small deviations from expected values, all during the same week, the week of perihelion. The deviations are within noise margins. Individually they're meaningless, but collectively they form a pattern. Or imagine spacecraft telemetry logs showing timestamp anomalies. Mars orbiters, Jupiter probes, ground-based receivers, all recording signals that arrived slightly earlier or later than expected. Again within error margins, but correlated, synchronized, as if something was affecting signal propagation across the solar system during that specific window. What would that mean? Could it be a glitch in the instrumentation? Sure. Could it be a calibration error? Absolutely. Could it be random noise that happens to cluster by coincidence? Yes. Or could it be a hint that our understanding of time measurement is incomplete? That there are environmental effects we haven't accounted for? That an interstellar object passing through our local space creates disturbances we can't model? I'm not claiming this happened. I'm exploring what it would mean if it did. Because if timing anomalies were detected and correlated with 3i Atlas, that would be extraordinary. Not proof of anything artificial, but proof that the universe can still surprise us. Proof that our instruments, our models, our assumptions are not as robust as we believe. And that's the essence of a black swan. It's not about predicting the unpredictable. It's about recognizing that unpredictability exists, that systems are more fragile than they appear, that rare events happen more often than theory suggests, and that when they do, the consequences can be irreversible. So which of these scenarios is real? Which remain plausible? Which are ruled out by data? We're about to find out. Because the story of 3i Atlas is still unfolding, and the only way to know whether we're inside a Black Swan event is to keep watching, keep measuring, keep questioning, until the picture becomes clear, or until it's too late to matter. Part 10. Cross-cutting. Mystery. What if it's already changing our understanding? Let's step back and assess. We've explored 8 scenarios, some grounded in orbital mechanics, some speculative, some borderline paranoid. But now we need to organize them. We need to evaluate their plausibility, their potential impact, and whether any evidence supports them. Because without a framework, we're just collecting fears, and fears without analysis are useless. So here's a simple table. Imagine it. For each scenario, we assign a plausibility rating: low, medium, high. We assess potential impact on science, on risk, on paradigm. And we note whether any current evidence exists. Not proof, just hints, observations that don't conclusively rule it out. Orbital domino. Plausibility? Medium. We know gravitational perturbations happen. We know orbits are chaotic over long timescales. We know 3i Atlas passed near Mars and will pass near Venus and Jupiter. Potential impact? High. A delayed cascade could seed future. Collision risks decades from now. Evidence? None yet. But absence of evidence isn't evidence of absence. The timescales are too long. The perturbation's too subtle. Fragmentation event. Plausibility? Medium. Comets fragment regularly. An anomalous fragment isn't impossible. Potential impact? Medium to high. Depends on the fragment's behavior. If it shows directed motion, that's paradigm shifting. Evidence? No confirmed fragmentation as of perihelion. But follow-up observations are ongoing. Solar disruption. Plausibility? Low. No known mechanism for a comet to trigger solar activity. Potential impact? High. A major CME during perihelion would affect Earth's infrastructure. Evidence? Would need to check solar activity logs for late October 2025. If a CME occurred, timing would be striking. If not, scenario loses credibility. Artificial signal. Plausibility? Very low. Requires extraordinary assumptions. Potential impact? Extreme. Would confirm extraterrestrial intelligence. Would rewrite human history. Evidence? None publicly acknowledged. But archival data may not have been fully analysed with that hypothesis in mind. Atmospheric anomaly. Plausibility? Low to medium. Depends on whether Comet Comet intersected Earth or Mars' magnetosphere. Potential impact? Low to medium. Would suggest unexpected particle interactions. Evidence? Unknown. Would require checking ionospheric monitoring data and Mars orbiter logs from early October. Disclosure cascade. Plausibility? Low to medium. Coordination is normal. Hidden anomalies would require intentional withholding. Potential impact. Medium. Would affect trust in space agencies. Would suggest prior detections were unannounced. Evidence? Circumstantial. EIWN campaign is public. Other data releases would need investigation. Psychological singularity. Plausibility. Medium. Social dynamics are unpredictable. Belief-driven consequences are historical fact. Potential impact. Medium. Real-world policy shifts. Funding changes. Public anxiety. Evidence? Observable in media coverage and social media trends, already occurring to some degree. Reality glitch. Plausibility? Very low. Requires unknown physics or systematic instrumentation error. Potential impact? Extreme. Would challenge fundamental assumptions about time measurement and signal propagation. Evidence? None. Would require deep archival analysis of timing data from multiple independent sources. So what does this tell us? Most scenarios are low probability. Some have plausible mechanisms but lack evidence. A few are already manifesting in subtle ways like psychological singularity. And one or two, like orbital domino and fragmentation, remain genuinely possible over long timescales. But here's the meta question. If 3I Atlas is normal enough, if it's just a comet with unusual but explainable chemistry, why is it still pushing the edge of our models? Why are scientists still debating its behaviour? Why are we entertaining exotic hypotheses at all? Maybe because the models aren't as complete as we thought. Maybe because interstellar objects represent a new regime, a new parameter space where our assumptions break down. Maybe because the universe is reminding us that normal is a statistical construct, not a law of nature. And if it's abnormal, if it's genuinely outside our models, do we have the systems in place to detect or respond? Planetary defense networks track near-Earth asteroids, but they're not designed for interstellar visitors. SETI listens for signals, but not from comets. Space agencies monitor solar activity, but they don't correlate it with small body passages. Our systems are siloed, specialized, built for known threats, not for surprises. So should astronomers treat interstellar visitors as potential black swans by default? Should every Oumuamua, every Borisov, every 3I Atlas get the full suite of observations? Radio scans, infrared spectroscopy, radar, photometry, trajectory monitoring for years after perihelion. That would be expensive. It would require coordination. It would mean diverting resources from other research. But what's the cost of not doing it? What's the cost of missing a signal because we didn't look? What's the cost of ignoring a perturbation that cascades into a threat decades later? The risk-reward trade-off is asymmetric. The downside of overcaution is waste. The downside of undercaution is catastrophe. And here's the uncomfortable truth. We might already be inside the event. The black swan might already be unfolding, slowly, subtly, in ways we won't recognize until it's complete. Because that's how these events work. They don't announce themselves. They don't wait for confirmation. They just happen. And we scramble to understand afterward. So what are the decision points? What measurements still matter? Post-perihelion brightness evolution. Is it decaying as expected? Is there a secondary peak suggesting fragmentation? Non-gravitational acceleration updates. Is the comet deviating from its predicted trajectory? Radio telescope follow-up. Has anyone scanned it for signals? Archival data sweeps. Are there timing anomalies in spacecraft telemetry, ionospheric monitoring? Were there disturbances during the close approaches? Each of these measurements is a thread. Pull one thread, and maybe nothing unravels. But pull enough threads, and maybe a pattern emerges. A pattern that wasn't visible before, a pattern that changes everything. And that brings us to the final point. 3I Atlas isn't the only weird thing in the sky. It's not the only anomaly challenging our assumptions. It's not the only object making scientists ask uncomfortable questions. There are others. Fast radio bursts with inexplicable properties, trans-Neptunian objects with bizarre orbits, quantum experiments showing timing residuals, AI-driven discoveries revealing patterns humans missed. The universe is full of loose threads, and maybe, just maybe, they're all part of the same tapestry. Part 11. Fast radio burst, repeating FRB oddities. Let's shift our gaze, away from comets, away from the solar system, out into deep space where pulses of radio energy explode from the darkness. Fast radio bursts, FRBs, one of the most mysterious phenomena in modern astrophysics, and one that might, in a strange way, be connected to the story of 3I Atlas. Fast radio bursts are exactly what they sound like. Brief pulses of radio emission, milliseconds long, incredibly bright, visible across billions of light years. The first one was discovered in 2001, buried in archival data from the Parkes telescope. But it wasn't recognised as significant until 2007. Since then, we've detected hundreds, maybe thousands, depending on how you count. Most FRBs are one-offs. They flash once and never repeat, but some do repeat. And the repeating ones are especially strange, because repetition suggests a persistent source, not a catastrophic event like a supernova, but something that can fire over and over, a neutron star maybe, a magnetar with extreme magnetic fields, or something else, something we haven't thought of yet. Let me give you a recent example, FRB 22100108A, discovered in 2022. Repeating, but not randomly, it shows periodicity. The bursts cluster in active windows, then go silent, then cluster again. The periodicity suggests rotation, maybe a neutron star with a hotspot. Every time the hotspot rotates into view, we see a burst. That's the leading theory. But here's the problem. The bursts don't fit standard magnetar models perfectly. The frequency structure is odd. Some bursts sweep from high frequency to low, others don't. The polarization rotates in ways that are hard to explain, and the energy output is enormous, equivalent to the sun's output over decades compressed into milliseconds. We're talking about objects the size of cities unleashing unimaginable power. So are FRBs natural? Almost certainly. Are they fully explained? No. And that's where the connection to 3I Atlas becomes interesting, because both objects challenge our models, both push the boundaries of what we consider normal, both invite speculation about exotic physics or even artificial origins. Imagine this. What if 3I Atlas emitted a radio pulse during perihelion? A brief burst. Micro-FRB. Not powerful enough to be detected across galactic distances, but strong enough to be picked up by nearby radio telescopes if they were pointed in the right direction. What would we see? A millisecond pulse, broadband or narrowband, maybe with frequency structure, maybe polarized. Would we recognize it as an FRB, or would we dismiss it as interference? The thing about FRBs is that we see them because we're looking for them, because we've built detection pipelines, because we scan large areas of sky continuously. But comets, nobody points radio, telescopes at comets looking for FRB-like emissions. Why would they? Comets are icy rocks. They don't generate the magnetic fields necessary for coherent radio emission. They don't have the energy sources. They're passive objects that reflect and scatter sunlight. Nothing more. But what if that assumption is wrong? What if under certain conditions, a comet's ionized coma can generate radio emission? What if the interaction between solar wind and cometary plasma creates instabilities, magnetic reconnection events, coherent radiation? These are speculative ideas, but they're not impossible. Plasma physics is complex, non-linear, full of surprises. Or, in the more provocative interpretation, what if an FRB detected in the vicinity of 3I Atlas wasn't generated by the comet, but was timed to coincide with it? A signal from elsewhere, deliberately synchronized, using the comet as a marker, as a beacon. That's wild speculation. But it's the kind of speculation that becomes less wild if you find a correlation. And here's the observational challenge. FRBs are detected by all-sky monitors, instruments like CHIME in Canada or ASCAP in Australia. These telescopes don't target specific objects, they scan large patches of sky. So if an FRB occurred near 3I Atlas, it would show up in the data. But correlating it to the comet would require someone to look, to check whether any FRBs detected in October 2025 came from the comet's position on the sky. Has anyone done that analysis? I don't know. Maybe, maybe not. But if they did, if they found even one FRB coincident with the comet's trajectory, that would be extraordinary. Not proof of anything, but extraordinary. Because it would suggest that we've been missing a class of events. Micro-FRBs, local FRBs, emissions that don't travel across the universe but occur within the solar system, or just beyond. Now, let's zoom out. Let's think about observational bias. We discover what we're looking for. CHIME detects FRBs because it's designed to detect FRBs, but it filters out signals that don't fit the template, signals that are too long, too short, too weak, too strong. It's optimized for extragalactic bursts, not for local anomalies. So what if there's a whole class of radio transients we're missing? bursts from comets, bursts from asteroids, bursts from interplanetary dust clouds, emissions that occur when charged particles interact with magnetic fields in unexpected ways. We wouldn't see them because we're not looking, and we're not looking because we assume they can't exist. That's the danger of models. They tell us what to expect, and what to expect becomes what we see. Everything else gets filtered as noise, dismissed as error, buried in archives, until someone revisits the data with new eyes, new algorithms, new hypotheses, and suddenly the noise becomes signal, the error becomes discovery. So here's my question. Should we start correlating FRB detections with interstellar object passages? Should we cross-reference sky positions and timestamps? Should we search archival data for coincidences? Because if coincidences exist, if there's even a weak correlation, that changes everything. It means these objects aren't as inert as we thought. It means the universe is more active, more interconnected than our models suggest. And it means 3i Atlas might be part of a larger pattern, a pattern we're only beginning to perceive. Part 12. Anomalous Solar System Object Discovery. Now let's bring it back home, back to our solar system. Because while we've been watching 3i Atlas, other strange things have been quietly accumulating in our catalogues. Trans-Neptunian objects with odd orbits, near-Earth asteroids with unexplained behaviour, and each one raises the same question. Are these isolated curiosities, or are they pieces of a puzzle we haven't assembled yet? Let me tell you about the Trans-Neptunian region. Beyond Neptune's orbit, roughly 30 to 50 astronomical units from the Sun, there's a population of icy bodies, the Kuiper Belt. Pluto is the most famous resident, but there are thousands of others, maybe hundreds of thousands, and their orbits tell a story. Most Kuiper Belt objects orbit in a relatively flat disk. Their orbits are circular or mildly elliptical. They're stable, predictable, but some aren't. Some have orbits tilted at extreme angles. Some have perihelia that bring them much closer to the Sun than expected, and some cluster in ways that seem non-random. This clustering led to the Planet 9 hypothesis, the idea that a massive planet, roughly 5 to 10 times Earth's mass, orbits in the distant solar system, far beyond Neptune. Its gravitational influence shepherds these distant objects into aligned orbits. It explains the clustering, it explains the tilts, it explains anomalies that otherwise seem like statistical flukes. But Planet 9 has never been observed directly. It's inferred, a ghost in the data. Some astronomers believe it's real, others think the clustering is observational bias. We find more objects in certain regions because we've looked there more often. The debate continues, and every new discovery either strengthens or weakens the hypothesis. Now, let me give you a specific example. A trans-Neptunian object discovered recently. Let's call it 2025 TN-113. Its orbit is bizarre, highly elliptical, perihelion at roughly 40 astronomical units, aphelion at over 1,000, orbital period of tens of thousands of years, and its inclination is extreme, over 60 degrees relative to the ecliptic. How did such an orbit form? Gravitational scattering by Neptune, maybe? An encounter billions of years ago that flung it outward? Or gravitational influence from Planet 9? Or something else? A passing star? A rogue planet? An encounter we can't reconstruct because it happened too long ago. But here's what's interesting. When you plot the orbits of these extreme trans-Neptunian objects, they don't scatter randomly. They cluster. Their arguments of perihelion align. Their longitudes of ascending node cluster. That's suspicious, because random scattering shouldn't produce alignment. It should produce chaos, unless there's something out there. Something massive, something unseen, shepherding these orbits, or unless the alignment is an artifact, a trick of observation, a consequence of when and where we've pointed our telescopes. The jury is still out. But the fact that we're still debating it means our understanding is incomplete. We don't know what's out there. We don't know what shaped the architecture of the outer solar system, and that uncertainty is where black swans hide. Now let's connect this to 3i Atlas. Both are oddballs, both challenge expectations, both raise questions about what's normal and what's not, and both highlight gaps in our population models. We thought we understood comets, we thought we understood trans-Neptunian objects, but when you look closely, when you examine the outliers, patterns start to dissolve, and you realise that normal is just the part we've measured most often. So are these oddballs isolated incidents? Or are they signs of something systematic? Maybe there's a population of interstellar visitors we haven't detected yet. Objects that pass through the solar system regularly but are too faint or too fast to notice. Maybe there's a population of extreme Kuiper Belt objects shaped by encounters we don't understand. Maybe the solar system is messier, more chaotic, more surprising than textbooks suggest. And here's the kicker. If these objects are part of a pattern, if they're connected by some underlying process, we won't see it until we have enough data, until we've catalogued enough outliers, until someone runs a statistical analysis and finds a correlation. And by then, the pattern will seem obvious. We'll wonder why we didn't see it before, but we didn't see it because we weren't looking for it, because our models told us not to. That's the nature of discovery. You find what you seek, and you miss what you don't. The question is, what are we missing right now? What patterns are hiding in plain sight? And will we recognize them before they become critical? Or will we only understand them in hindsight, when it's too late to prepare? Part 13. Quantum Physics Anomaly News. Let's venture into even stranger territory. Fundamental physics, the bedrock of our understanding. The constants and laws we assume are universal, unchanging, eternal. But what if they're not? What if the universe is more fragile, more mutable, more surprising than we thought? In 2024, a paper appeared on the Arxiv preprint server suggesting a possible anomaly in the fine structure constant, alpha. This constant describes the strength of electromagnetic interactions. It shows up everywhere in physics, atomic spectra, quantum mechanics, electromagnetism, and it's supposed to be constant. The same everywhere in the universe, the same at all times, but the paper analysed quasar spectra from distant galaxies, light that has travelled billions of years to reach us, and it found hints, very slight hints, that alpha might have been different in the early universe, different by parts per million. Not much, but enough to be statistically interesting, if real. The physics community is divided. Some think it's a calibration error, some think it's systematic bias in the data, some think it's real and revolutionary. The debate continues. More data is needed, better measurements, independent confirmation. But the possibility lingers, the possibility that constants aren't constant, that the universe evolves in ways we don't understand. Now, let's talk about timing residuals. Pulsars are the most precise clocks in the universe. Neutron stars rotating hundreds of times per second. Their pulses are so regular you can set your watch by them. Astronomers use pulsar timing arrays to detect gravitational waves. They measure the arrival times of pulses from dozens of pulsars, and they look for correlated deviations caused by space-time ripples from distant black hole mergers. But sometimes, the deviations don't correlate. Sometimes, individual pulsars show timing residuals that can't be explained. Noise, probably, instrumental error, interstellar medium effects. But sometimes, the residuals are too large, too persistent, too strange, and you start to wonder, what if there's something else? What if space-time is noisier than we thought? What if there are glitches, fluctuations, anomalies that we haven't modelled? Now, connect this to 3i Atlas. Connect it to the reality glitch scenario. If fundamental physics has wrinkles, if constants aren't perfectly constant, if timing systems are less robust than we assume, could an interstellar object passing through the solar system highlight those wrinkles? Could it interact with the local space-time fabric in ways that reveal underlying instabilities? I'm not saying 3i Atlas distorts space-time. Its mass is too small, its gravitational field is negligible. But what if it's passing through a region where space-time is already slightly anomalous? A region with higher than average dark matter density? A region influenced by a passing gravitational wave? A region where, for whatever reason, physical constants are minutely different? If that were true, instruments observing the comet might detect anomalies, timing offsets, spectral shifts, trajectory deviations that don't fit Newtonian or relativistic models. Not because the comet is exotic, but because the environment is exotic, and we don't have the resolution to see it yet. This is speculative, wildly speculative, but it's grounded in real questions about fundamental physics, questions that experiments like the Large Hadron Collider, the dark energy, survey and pulsar timing arrays are actively investigating, because the more precisely we measure the universe, the more we find anomalies, small deviations, edge cases, outliers that don't fit the standard model. And every outlier is either an error or a discovery. The challenge is figuring out which, because errors are common, discoveries are rare, and distinguishing between them requires rigor, replication, independent confirmation. But sometimes you only get one chance, one measurement, one object passing through, and if you dismiss it as error, you might miss the discovery. But if you claim it as discovery, you might be wrong. And wrong is embarrassing, careless, career-ending. So scientists err on the side of caution. They demand high confidence, multiple sigma, reproducibility, and that's good, that's necessary. But it also means we're biased toward missing discoveries, toward filtering out the truly anomalous as noise, toward playing it safe at the cost of missing the revolutionary. And that brings us back to the central question. Are we looking at 3i Atlas with the right tools, with the right hypotheses, with the right openness to surprise, or are we fitting it into existing models because that's comfortable, because that's what we're trained to do, because admitting we don't understand is harder than pretending we do? I don't have answers, but I have questions, and questions are the beginning of science, the beginning of discovery, the beginning of understanding, and if 3i Atlas teaches us anything, it should be this. The universe is still capable of surprise, and we should be ready for it. Part 14, AI-driven signal and pattern detection breakthrough. Science today is both overwhelmed and empowered by its own success. Every night, our instruments flood us with more information than any generation in history could dream of handling. Telescopes sweep across the sky, generating terabytes of data before dawn. Satellites orbiting Earth transmit continuous streams of measurements, from temperature to radiation to magnetospheric flux. Particle accelerators record billions of collisions per second, each collision a potential key to understanding the fabric of reality itself. And yet, we can't see it all. We can't look at every image, can't check every spectrum, can't analyze every line of code that describes the universe back to us. The flood of data has outpaced the human brain, so we automate. We build algorithms to sort the noise, to highlight what we already believe matters. We design filters to eliminate false positives, to reduce complexity. We trust the machines to find the familiar and discard the rest. But what happens when the truth hides in the discarded? What if the signal of the century, the anomaly that redefines physics itself, is something our filters quietly removed, because it didn't fit a pre-existing pattern? That's where artificial intelligence changes, the story. Machine learning doesn't just follow instructions, it learns from data. Instead of rigid filters, it adapts. It identifies patterns we can't describe in equations, sees structures we can't visualize, and notices deviations we can't rationalize. It doesn't know what it's looking for, and that, paradoxically, is its strength. In the last few years, AI has started to make real discoveries. Not simulations, not theoretical predictions, actual, verifiable, scientific findings. Take the Kepler Space Telescope. Between 2009 and 2013, Kepler stared at more than 150,000 stars, recording their brightness every few minutes in search of transiting exoplanets. The mission's official pipeline found thousands of worlds, but it was optimized for the predictable, regular dips in brightness, periodic orbits, clear, strong signals. But the universe doesn't always behave regularly. In 2023, a team of researchers applied deep learning to the old Kepler data, training neural networks not on theoretical models, but on the data itself. The AI wasn't told what a planet's signature should look like, it simply learned what different looked like. The result? A handful of new planets the original algorithm missed, including ones with irregular or quasi-periodic transits, where orbits are perturbed by neighbouring bodies or tilted by gravitational resonance. The AI even found potential exomoons, objects that cause subtle asymmetric dips that human-designed code had dismissed as noise. That's the quiet revolution underway. AI isn't replacing astronomers, it's showing them what they never thought to ask. The same pattern appears in other fields. Consider galaxy morphology, the way we classify galaxies into spirals, ellipticals, or irregular shapes. For decades, classification was manual, sometimes even artistic. Then came Galaxy Zoo, where volunteers around the world categorized millions of galaxies by hand. But AI can analyze tens of millions overnight, and when researchers turned it loose on the Sloan Digital Sky Survey data, it started finding outliers, galaxies that didn't fit any known shape. Some looked like collision remnants, others resembled gravitational lens artifacts or ghost images of galaxies behind galaxies. Each anomaly hinted at new astrophysical processes. The AI wasn't just reproducing human knowledge, it was expanding the taxonomy of the universe itself. Now imagine applying this same logic to 3I Atlas, the interstellar object that has everyone talking. It's not behaving like a normal comet. Its acceleration patterns are strange, its tail dynamics shift unpredictably, its albedo changes don't match standard outgassing models. So, what if we fed all the available data into a neural network? Every photometric light curve, every spectroscopic reading, every trajectory log, every polarimetric profile, and every image metadata set collected from observatories worldwide. Then ask the AI a simple question. What doesn't fit? No assumptions, no models, just pattern recognition. Maybe it would find brightness fluctuations repeating every 6.3 hours, too regular for coincidence, too erratic for simple rotation. Maybe the amplitude drifts subtly over time, suggesting a secondary periodic modulation, perhaps a binary rotation or an active core responding to internal heat cycles. Or maybe the AI would discover something deeper, a correlation between outgassing jets and non-gravitational acceleration, but one that doesn't follow standard physics. Perhaps the thrust vectors are asymmetric in a way that implies directed emission, as if something is steering the ejected material, not merely venting it. None of it would be conclusive, but all of it would be interesting, and that's where discovery begins. AI has one superpower. It notices. But it has one fatal flaw. It doesn't understand. It can't tell noise from novelty, coincidence from causality. It flags anomalies, but it's up to humans to decide whether those anomalies matter. And humans, for all our brilliance, are biased. We crave patterns. We see faces in clouds, gods in thunder, intent in randomness. In science, our bias works both ways. We sometimes invent meaning where none exists, or reject meaning because it seems too strange. So the answer isn't to trust AI blindly, it's to verify. Run the same analysis across independent datasets, use multiple models, cross-check results with different instruments. If the signal persists, if it appears under different conditions, with different algorithms using different assumptions, then, and only then, do we start to believe. Replication is the antidote to illusion. Has anyone already done this? Has someone somewhere fed the full 3I Atlas dataset into a deep learning model? Maybe a graduate student at JPL, maybe a hobbyist running TensorFlow on a home GPU cluster, maybe a national lab that doesn't talk about its projects publicly. Maybe the analysis is happening right now, and no one outside that small circle knows what's been found. Or maybe, incredibly, no one has tried. Maybe our greatest cosmic anomaly is slipping through our fingers because no one thought to let the machines look. If that's true, it's a missed opportunity of historic scale. This is what the future of astronomy looks like. Human intuition plus machine perception. A partnership between theory and data. We build the models. The AI breaks them. We interpret the findings. The AI finds what we can't imagine. In the coming decade, as observatories like the Vera Rubin Observatory, LSST, come online, producing 20 terabytes of sky data every night, there will be no other choice. Human analysis alone won't scale. The universe will demand algorithmic curiosity, and in that world, discovery will no longer mean stumbling upon something unexpected. It will mean training the machine to see what we've trained ourselves to ignore. Here's where it comes full circle. A Black Swan event in space isn't just a surprise. It's something so far outside expectation that our entire framework of understanding must change to accommodate it. But how can we detect the truly unexpected if we only ever look for what we expect? That's the paradox of modern science. The better our instruments, the narrower our vision becomes because we drown in precision. We filter, we automate, we limit. AI could be the key that breaks that loop, because if 3I Atlas is anything, a natural oddity, a misidentified interstellar relic or something altogether stranger, it's a test of our ability to see beyond our models, to see without knowing what we're looking for. And if an AI someday finds something in its data, something we can't explain, something we can't replicate, something that challenges physics itself, that will be the truest black swan of all. A discovery made not by humans looking for meaning, but by a machine finding what meaning couldn't imagine. Somewhere, in a server room, humming quietly under white light, petabytes of sky data sit waiting, invisible to the human eye, yet filled with secrets. An algorithm will wake, sift through the noise, and perhaps, just perhaps, notice a flicker that no one else did. A pixel too bright, a curve slightly off, a pattern that doesn't fit. And from that whisper of data, a question will emerge. Is this just noise, or did the universe just blink? That is the age we're entering. The age where machines watch the cosmos, not for us, but with us. And when the next anomaly, like 3I Atlas, arrives, it won't just test our science. It will test our ability to listen to what the machines are trying to tell us. Part 15, Final Reckoning and Looking Forward. So here we are, 15,000 words into an investigation of a comet that might be nothing, or might be everything. 3I Atlas, an interstellar visitor that arrived in July 2025, that outgassed when it shouldn't. That showed chemistry we've never seen. That passed perihelion on October 29th and is now receding into darkness, fading from view, slipping back into the void from which it came, and the question remains, is this simply a strange comet, or is it a dormant black swan waiting to unfold? Let's revisit the scenarios. Orbital domino. Plausible over decades. No way to rule it out, no way to confirm it yet. We'll only know if something unexpected happens years from now. Fragmentation event. No confirmed fragmentation as of now, but perihelion stress could trigger delayed breakup. Follow-up observations continue. Solar disruption. No major solar events coincided with perihelion. Scenario loses credibility. But the question remains valid for future visitors. Artificial signal. No confirmed detection. Archival searches ongoing. Low probability but high stakes. Atmospheric anomaly. Unclear. Data exists. Analysis needed. Disclosure cascade. Possible. Subtle. Invisible in real time. Psychological singularity. Already happening. Media coverage. Social speculation. Real consequences from perceived uncertainty. Reality glitch. No evidence. Wildly speculative. But philosophically interesting, so what remains plausible? Orbital perturbations. Fragmentation. Psychological effects. What's ruled out? Solar disruption, mostly. Artificial signals and reality glitches remain in the realm of, we haven't looked hard enough to say no. And that's the frustrating thing. Absence of evidence is not evidence of absence. Just because we haven't found something doesn't mean it's not there. So what happens next? What observations matter most? Post-perihelion brightness monitoring. Is the light curve decaying as expected? Any secondary peaks? Any unusual fading rates? Non-gravitational acceleration updates? Is the trajectory matching predictions? Any deviations as outgassing continues? Radio telescope follow-up. Has anyone scanned for emissions? Any archival signals detected? Spectroscopic analysis. How is the coma composition evolving? Any changes in the carbon dioxide to water ratio? Fragmentation monitoring. Any new components appearing? Any unusual morphology in high-resolution images? And then there's the archival work, the deep dives, the AI analyses, the cross-correlations, checking pulsar timing data, checking spacecraft telemetry, checking ionospheric logs, checking solar activity reports, checking FRB catalogues, looking for coincidences, looking for patterns, looking for anything that might connect 3I Atlas to broader anomalies. Some of this work is happening, some isn't. Some won't happen because nobody thought to do it, and that's the tragedy of missed opportunities. Because once the comet fades, once it's too dim to observe, the window closes. The data becomes fixed, the archives become final, and we're left with whatever we captured, whatever we prioritized, whatever we thought was important at the time. But here's the thing, even if 3I Atlas is completely normal, even if every anomaly has a mundane explanation, it still taught us something. It's reminded us that interstellar visitors are real, that they can have chemistry unlike anything in our solar system, that they challenge our models, that they demand our attention, and that we need better systems for detecting and characterizing them, because they're going to keep coming. 1I/Oumuamua was the first, 2I/Borisov was the second, 3I Atlas is the third, and there will be more, many more, maybe dozens per year once our detection systems improve, maybe one per month, maybe one per week, and each one will be different. Each one will carry information about its parent star system, about the conditions in interstellar space, about the diversity of planetary formation processes across the galaxy, and some of them, maybe, will be black swans, objects that don't fit any category, that break our models, that force us to revise fundamental assumptions, objects that are artificial, or intelligent, or revealing of physics we don't yet understand, low probability, but non-zero. And non-zero is all you need for a black swan. So what are the implications? If 3i Atlas is a black swan, what happens? Scientifically, paradigm shift. New physics, new understanding of cometary activity or interstellar object populations or something else entirely. Practically, planetary defense gets re-evaluated. We start tracking interstellar visitors more carefully. We build better detection systems. We coordinate internationally. Culturally, perception shifts. Space becomes less predictable, less safe, more mysterious, more worthy of caution and wonder. But if it's not a black swan, if it's just a comet, what then? We learn humility. We learn that the universe is full of statistical outliers. That rare doesn't mean impossible. That weird doesn't mean artificial. We refine our models, we expand our parameter space, we get better at distinguishing between anomaly and error, and we prepare for the next object, and the one after that. Either way, we benefit. Either way, we learn. Because that's what science does. It transforms uncertainty into knowledge. It converts mystery into understanding. Not perfectly, not completely, but incrementally, persistently, over time. And here's my final thought. If the sky can still surprise us like this, if an interstellar comet can generate this much speculation, this much analysis, this much wonder and fear, then what else has been hiding all along? What else are we missing? What other anomalies are buried in our archives? What other patterns are waiting to be found? What other black swans are circling, invisible until the moment they land? We live in an age where telescopes scan the entire sky every night, where satellites monitor Earth continuously, where experiments probe the fundamental structure of reality. We have more data than ever before, more instruments, more computing power, more ability to detect the unexpected, and yet we're still surprised, still puzzled, still asking questions we can't answer. That should excite us. That should terrify us, because it means the universe is not finished teaching us. It means our models are incomplete. It means there are discoveries waiting, black swans waiting, events that will rewrite textbooks, that will shift paradigms, that will change everything we thought we knew. 3i Atlas might be one of those events, or it might not. But the fact that we can't be certain, the fact that we have to consider the possibility, that alone is significant. Because it means we're finally taking the unpredictable seriously. We're finally acknowledging that space, for all our satellites and telescopes and missions, is still mostly unknown, still mostly mysterious, still capable of delivering shocks we can't anticipate. And if that doesn't keep you awake at night, staring at the stars, wondering what's out there, what's coming next, what we've already missed, then you haven't been paying attention. Because the message of 3i Atlas is not that the sky is falling, it's that the sky is awake and watching, and full of possibilities we can barely imagine. So keep looking, keep questioning, keep wondering, because somewhere out there another object is approaching, another anomaly is waiting, another black swan is gliding silently through the darkness, and when it arrives, when it finally reveals itself, we'll have only one question. Did we see it coming, or were we looking the other way,